Thanks for coming. Today I'm going to talk about our work, Compass, in which we explore strong and compositional specification for relaxed memory libraries in separation logic. So let me jump right into a example client that we want to verify, and which also requires strong specification for a relaxed memory library. So the library here is a concurrent queue, and we have a client with 3 threads using the queue. In thread 1 is simply to perform 2 NQs, and in the other 2 threads, each will perform a single DQ. Right. As of now, you can see that without coordination among the threads, it is possible that both of the DQs by thread 2 and thread 3 will return empty. Right. So suppose we, as a client, want to exclude the case where the DQ in thread 3 return empty. We might try to do so by introducing some synchronization between T1 and T3 by using an extra atomic location flag. And the way it works is that T1 simply perform the 2 NQs, then set the flag, and T3 wait for the flag to be set, and only then execute its DQ. Right? The question is this actually sufficient? If you look at this in a sequential consistency setting, then this is actually easy to see. But it's quite tricky to get this in relaxed memory. In particular, we would have some strong specification for our queue library, such that it can help exclude the empty DQ case in thread 3. And the reasoning is that the DQ by thread 3 will guarantee to do something good, in this case, successfully DQ some element, if it somehow knows that the environment, in this case, T1 and T2, is also doing something good, meaning that it see that, well, T1 has at least performed 2 NQs and T2 will not consume more than 1 NQ, so there's still one NQ left for it to DQ, and so we will not return empty. Right. So generally, what we really want is we want to have strong specification for relaxed memory library that not only take into account the relaxed behavior of the library itself, but also how the environment, for example, the extra client synchronization, can interact or influence the such relaxed behaviors. And furthermore, we want to do this in separation logic so that we can take advantage of the modular verification support and also mechanization support in previous work. Unfortunately, such strong separation logic specs didn't exist before, and this is what we aimed to work at in this work. And the way we did it is that we first look at the concurrency verification literature and see how can you prove strong specifications in a sequentially consistent separation logic, and how can we reuse that existing approach for relaxed memory. And so if you are familiar with concurrency verification literature, you will think that, oh, maybe I can prove that my data structure is linearizable, which means that you show that each of the function calls to the concurrent object will have a linearization point, and you can give a total order on those linearization points. In other way, construct the linearizations, and then you get to specify the property of your concurrent object. You can prove linearizability directly with our logic, but you can also use logical atomicity to prove linearizability from within a concurrent separation logic, and also take advantage of the modular verification support from separation logic. And the way that you would do that is that you verify in the separation logic, your data structure satisfies some logically atomic triples. And in this case, I'm showing you 2 triples, 2 logically atomic triples for sequentially consistent queue. Right? And the point is that these are not the traditional triples. It's using the angle brackets, which mean that these pre and post condition here are the pre and post condition around the linearization of the function call, instead of around the whole execution of the function. And so it means that you can compose these things so that you can use logical atomicity to perform fine-grained concurrency, while you can still get the familiar sense with working with sequential specs. Right? So this is nice. And we want to use also logical atomicity for relaxed memory. And for that purpose, in this work, I want to take a closer look into this spec of DQ. Well, okay, I skip a step. That's too fast. But let me explain the idea of logicality here. In the DQ here, what it is saying is that around the linearization point, the precondition is that the Q has a list of value Vs, and it will the function will atomically update the state Vs into the state Vs prime, which is the tail of Vs, in the case that the Q the DQ successfully returns some element, which is the head of the QV. In the failing case, it will return empty. And the spec here is saying that it knows that if the DQ return empty, it must have been the case that at the linearization point, the Q must exactly be empty. This is a very strong property. And if we use the property, we can actually show our motivating example in the context of a sequentially consistent semantics. However, this property is indeed too strong for relaxed memory implementation. And the intuition is that a relaxed DQ may have only observed some stale empty state of the queue. And with that, it can simply just return empty, even though at that point the queue wasn't really empty. Right? So what we set out in this work is that we want to use logical atomicity, but we want to, in a way, relax these specs so that it works for relaxed memory. And we observe that logical atomicity is not necessarily tied to sequential consistency or linearizability. And so we propose in this work is to combine logical atomicity with many relaxations of linearizability that have been proposed in previous work. The ideas of these relaxation of linearizability is that instead of requiring a total order on the library's operations, we can instead require certain shape of the partial orders on the library operation to specify their correctness. And as the result of this combination, we present Compass, which is a framework to specify strong properties and compositional property for library in relaxed memory. And Compass is a framework that extends the existing relaxed memory separation logic IRC11, which work for the RC11 memory model. And in this work, we explore several kinds of specs and study their simplicity versus expressiveness. But I don't have time to go into detail here. The important point is that, well, we have a lot of specs and proofs, and some of them are the first ever proposed in separation logic. And more importantly, all of these are done, are mechanized in the concurrent separation logic framework IRIS in Kong, which IRC11 was built on also. So in the rest of the talk, I'm going to give you a very quick taste of how the Compass specs for relaxed memory look like and what they can be useful for. In particular, they can be useful to verify our motivating example. So this is a simplified version of a logically, an instance of logically atomic specs with partial order for relaxed memory queues. And there are quite a lot of things going on here. I just want to point out some of the basic ingredients in the spec. I'm not going to explain any detail much. Very obviously, what we're seeing is that we are using these logical atomic triples in the angle brackets. So yeah. And then secondly, we want to use partial orders to restrict the desirable behavior of our data structure. So in this case, what we need to do first is that we track the linearization response of the, say, queue operations as events. And then there are partial orders between the events, and we track them in so-called an event graph, G, which is considered part of the state of the data structure. Yeah, very ugly. And finally, in order to restrict the operations, the behavior of the operations, we enforce certain invariants on these partial orders. Right. So that's the basic ingredients. So what exactly are these partial orders? Well, in general, the specifier can pick whatever partial order they want. But in relaxed memory, synchronization is a key property for correctness, and this is often formalized as the partial order happens before HB. And so we can think about exposing the synchronization generated by the data structure. For example, for the Q, it will be that the synchronization between an NQ and its matching successful DQ. Right? In fact, this is not a new idea. This has been done by Melville and Jordan in their work published in ICFP last year for the multi-core algorithmic memory model. And Jahan did give a talk yesterday. And the key point is that they expose the synchronization between matching NQs and DQs and among NQs and among DQs. But the general idea is that they expose the synchronization that is generated by the libraries itself, internally by the libraries itself. This is the first use of logical atomicity in the context of a relaxed memory separation logic. But the only exposing the internal synchronization generated by the library is not sufficient for an example like this. In fact, we don't really get any information from the specs by Melville and Jordan in the case that we have an empty DQ. And for our example, what we really care about is that in order to show that the DQ of T3 cannot return empty, we have to take into account that that DQ has already observed the two DQs made by T1, thanks to the synchronization created by flag. Right. In other words, what we really need is that we have to track the whole happens before relations between all of the library events, which include not only the internally generated one by the library, but also the externally generated, for example, by client synchronization. That's the basic idea. And so how does this show up in the spec? In order to track the external synchronization, the external happened before, we introduce specifically for the spec for the Q, a separation logic assertion scene Q. This basically track the external happens before relation. And the specs of these NQ and DQ both take in this scene Q assertion as a precondition, and then we use that to constrain the behavior of the function. And with that, our happens before relation that track in our event graph actually cover both the internal synchronization and the external synchronization. So the invariance that we enforce on the happen before actually allow us to state much more stronger properties. In particular, for our example, we have enforced some properties like this for the empty DQ case. And it say that, well, if there's an NQE that happens before an empty DQD, then there must exist another DQ, D prime, that's DQ from E, that's what matching means, but also happens before D. Now, this may not make much sense, but we can look at the diagram and see that this is actually a simple property. Assume that we have an empty DQ, and we know that there exists a NQ that happens before D. Then the invariance simply say, well, there must be another DQ, D prime, that's DQ from E, and happens before D. Very simple, right? And this is good enough. Well, actually more than enough. We don't really need this that strong. But this is more than enough to verify our motivating example. The idea here is that we set up some invariant, which I will not go into detail. But the first point is that T1, after performing its two NQs, it will be tracked into the scene queue assertion here. Remember that scene queue track that happened before of the client. And this can be transferred to T3 and be made available for T3 because before it's calling DQ. And then the caller T3 DQ can use the spec with the scene queue of the two NQ event E1 and E2 to exclude the empty case. right? And now we can invoke the invariant. In particular, let's assume that the DQ return empty. Well, we know that E1 and E2 happens before DQ. Then by the invariant, we know that there exists two other successful DQ, the DQ from E1 and E2, that they also happens before D3, right? But globally, we know that, well, there can be only two NQs, so contradiction. Yeah, but very simple, right? The idea is that there should be at least one NQ that I can use. So it cannot be that there are already two DQ. And with that, we can exclude the empty case and you can conclude the proof and conclude the talk. So here I presented to you Compass, a framework to give strong and compositional specification for relaxed memory library using rich partial orders, blah, logical specificity, blah, blah, blah. There's a lot of things in the papers. We explore a lot of specs. Some of them are simpler, some of them are way more complicated. And these are for target toward more relaxed libraries or libraries that can be linearizable. We have a lot of specs on different type data structures. We have to develop extension to the logic in order to state and even verify these specs. And well, a lot of more client verifications of these libraries. They are all in Iris and Core. Yeah, with that, thank you.
Thanks for the talk, really interesting. So I was wondering about the relaxed memory models that you would support with this. So this atomic plus partial orders, would that also work with non-multi-copy atomic models like Power or PTX?
Yes, I mean it's logical atomicity is not tied to sequential consistency or relaxed memory, but the point is that you can basically pick out the relaxed behaviors in the spec using the extension of the logics, and then you combine that with logical atomicity. So it will be just the difference between what it means to own something under some relaxed memory model, if that makes sense.
I would have a question. So you had you showed this long Q consistent definition or something like that, where they had this existential that gives us the extra event that must have been between the NQ and the empty DQ. So this looks like a bunch of properties that could in principle all derive from like the set of valid sequential traces. So is there some higher level way to get that, or some way to ensure I haven't forgotten the fifth and sixth consistency axiom or something like that?
Yes. So in the case where your library is strongly consistent enough, or is it linearizable, then you would not use these specs, because a simpler, stronger spec would imply all of these properties. But in the case that they are not, then what you see here is that actually these properties are actually much weaker. So something like the properties I was showing here, that you require that there must be a DQ that happened before D. It can be even weaker. It's not like, it will not be D prime happened before D, but it will be like not D happened before D prime. Right? They are very weak. So you will not get a simpler spec for these very relaxed implementations.
And I guess it's not automatic, because there's like design decisions there in terms of how many promises you still want to make.
Yeah.
All right. Well, let's thank Hai again. And let the next speaker set up, please.